or give you an introduction to the Belimo energy valve. If you're not familiar with this technology, the Belimo energy valve is an electronically pressure-independent control valve with a fully integrated and backnet connected BTU meter. That seems like an awful lot of stuff to jam into a control valve, but I'm going to spend the next 20 minutes or so trying to explain to you why we did that and how it can benefit you or your customer. So let's go ahead and start obviously with the title. The number one feature behind the Belimo energy valve is it allows us to address low delta T problems both in chilled water system and even in hot water systems where it's relevant. So let's go take a look at how that comes into play. If we take a look at delta T, we usually think about delta T problems as a plant problem. Our chiller plant has a low delta T, or our condensing boiler is not condensing because we can't get our return water cool enough because we're not getting enough delta T. Delta T is not caused at the plant, though. It obviously facilitates or it presents itself at the plant, but it is caused, well, for several reasons. But if we've corrected reasons of bypassing too much water or three-way valves or constant volume pumping, once we've gotten those things under control and we still have delta T problems, it's usually because we're having very inefficient heat transfer at our coil. And so what do I mean by inefficient heat transfer? Well, when we talk about inefficient heat transfer, what we mean is that we're using more water than we really need to offset the load in the space. Or a different way to say that is that we increase our flow rate but don't increase the amount of heating or cooling that's occurring in the space. And this concept is a little bit abstract for most folks, but I'm going to take a little bit of a look over the next few slides and try to explain to you how that happens. Certainly the result of pumping more water and not changing the load offset in the space would be that we require more pump horsepower to generate the increase in GPM. And then the lower delta T and increased flow tend to have a reduction in the efficiency of our plant, albeit whether it be in a chiller environment or, as we discussed earlier, there's benefits as well in condensing boilers. Let's go ahead and take a look at the heat transfer of a coil, and we can try to explain a little bit better why delta T is so important. What you're looking at here is a fairly typical coil characteristic. So we're increasing flow in GPM from left to right on the x-axis, and we're increasing BTUH, or power produced in that space, as we go up the y-axis. And you'll notice that the relationship between flow and BTUH is not linear. It's actually got a curved shape to it, and flow is actually much more heat transfer rather is much more efficient at low flows. So you can see down where we're about 10, 15 gallons a minute that the curve is significantly steeper there. So we're having significantly larger gains in BTU per increase in flow. So we might only increase the flow 10%, but we might get 20 or 30% more BTU at these low flow areas. And then as we get to higher and higher flows, we see less heat transfer per percentage increase in flow. And this just has to do with the physics of heat transfer. If the water's going through the coil faster and faster, it has less chance to exchange heat, and so that heat transfer process is less efficient. So this heat transfer is represented by the equation we see here. BTUH, or power output in the unit BTUH, is represented or calculated by 500 times the flow rate times delta T in degrees Fahrenheit. And so we have delta T in this formula as well. So power produced is a function of both flow and delta T. I'm going to go ahead and put delta T on this graph as well so we can see how that charts out. And delta T looks quite the opposite of our coil characteristic, but really for the same reasons. Our slow water is in the coil a long time and therefore has a high delta T, has a lot of chance to exchange its heat. And the faster we push water through there, the lower our delta T tends to get. This would be an ideal scenario that we're looking at now. If we truncated the flow of this coil as we see it here at about 55 gallons a minute, I would say we have a very efficient coil. But let's take a look at what happens if we intentionally or unintentionally overflow this coil. So let's go ahead and do that. So you could see here as this new data comes into play that three things happen to me that I don't really like when I overflow my coil. First, I have to generate extra pump head to get this extra flow through my coil. The second thing that happens is that my delta T continues to drop, so now we've developed this low delta T that we were talking about. And the most troubling thing is the third item on this list, which is that I'm not producing any more BTU. So the BTU output of this coil starts to plateau once we get past the design flow parameters of that coil. So if we take a look, for example, at the point illustrated here by this little black dot, and I extrapolate a line horizontally to all of the different flow values that produce the same amount of cooling, and in this case it's about 330,000 BTUH or so. All these different flow rates shown across this orange line produce the same amount of cooling in that space. So we had the ability, based on adjusting flow and delta T simultaneously, to produce the same load at lower flows or higher flows based on the efficiency of the heat transfer. Now, interestingly, this is not just a full flow problem, or symptom rather. We can take a look at this point here, which is much closer to, say, 260,000 BTUH, and we can still extrapolate a fairly sizable line. Now, I think we could probably all agree that this coil that we're looking at here is rather well behaved, and we're probably not going to do a whole bunch of delta T limiting at partial load, although we certainly could do delta T limiting at full flow and cut off the last few degrees of delta T that we lost. But let's take a look at a sloppier coil, something that's like this, and this is frankly much more typical of what you might see in the field. And let's take a partial load point here and extrapolate that line. And now we're looking at a massive range of flows in which we produce the same exact amount of cooling. And as we go from left to right and we look at the delta T points, they just start to plummet. So what we learn from this is that delta T is a really good indicator of the efficiency of our heat transfer. If we're looking at delta T and we're able to manipulate our delta T, we can force our coils to be more efficient. Now, it would be unfair for me to say that we could chop off everything to the right of that black point and say we never need to flow past, in this case, about 30 gallons a minute to produce that amount of cooling. That's not realistic, but we certainly don't ever need to be out in the 45 to 55 GPM range. So we're looking to cut off that very high flow area where we get very diminished delta T performance. Okay, so that brings us to the energy valve. What is this thing? Well, as I said at the beginning, it's an electronically pressure-independent valve with an integrated BTU meter, and it allows us to do a bunch of things. It allows us, obviously, to measure energy. We're putting a BTU meter on every coil now that has an energy valve. It also allows us to control power into our space, which I'll explain in a little bit, and we can manage delta T. The valve itself is made up of, frankly, a bunch of stuff that already existed. So we took a control valve. It is a large characterized ball valve on the front end of this particular energy valve. There's an actuator on the top. It is a 90-degree rotational actuator with an awful lot of smart technology built into it, but it still takes a 2 to 10 volt signal and rotates 90 degrees. So from the standpoint of the automation system, it looks just like a standard control valve. We have a flow sensor built into the backside. This particular valve carries a magnetic flow sensor. The smaller size energy valves include ultrasonic flow meters. We also incorporate a couple of temperature sensors to detect delta T. So one of them will be embedded in the valve, the other one gets plugged in on the other side of the coil so we can measure the differential temperature across that coil. And once we have flow and delta T, we can calculate BTUs. So remember, our BTUH formula was 500 times the flow rate times the delta T, and so we're able to get those here. So that's what makes our BTU meter. And then in addition to that, we made a BACnet capability for our energy valve, so you can communicate effectively. Now, it is not required that you use the BACnet. The Belimo energy valve is a standalone device, so it doesn't need to be networked anything past your standard analog control signal, but it does generate a large amount of data, and so we've offered a BACnet capability with it as well. So what are the true benefits of the Belimo Energy Valve? Well, we like to break them into three categories. The first one, and one that sort of garners the most attention, is the ability to save energy. The energy valve can actually allow you to cool your space or heat your space using less water to do the same amount of heating or cooling. And so we're going to do that with delta T management. It also simplifies the control of your building. Since the energy valve is a pressure independent valve, your system by its nature will become dynamically balanced, or any loop that contains an energy valve will be dynamically balanced. And the energy valve has the ability to control directly to flow or directly to power output. And thirdly, it allows us to track the performance of our equipment. So we're putting a BTU meter on every piece of equipment, and we can track that. So how are we saving the energy? Higher delta T means that we have more efficient heat transfer. What it really means is that I'm going to use less water to create the same amount of cooling. So what are we going to do there? We're going to define a low limit of acceptable delta T for a particular coil. So let's take a look at our kind of clean looking coil here, and we'll just say that we're going to define a 12-degree low limit. So what that does is that the valve will modulate normally in response to the automation system under all conditions unless the delta T drops below 12. So let's say that we have overflowed this coil. Let's say we're up at 64 gallons a minute. We've overflowed the coil. We're measuring a delta T in the 10.5 degree range, and we have mandated a 12-degree delta T. What's going to happen with delta T manager is that the control signal is going to be suspended from the automation system, and the valve will start to restrict its own flow. As it does that, we're going to see that the flow reduces, the delta T increases, and if we have selected a delta T limit appropriately, we won't see any diminishing of the cooling available to that space. So as you can see on this graph here, we've taken our delta T from 10.5 to 12 degrees F. We've moved our flow from 64 gallons a minute down into maybe the 52, 53 gallon a minute range, and we've produced essentially the same amount of cooling in that space. Delta T management is all about producing the same amount of cooling for less water. So that's what we're going to do from the energy management standpoint. How are we simplifying control? Well, an electronic pressure independent valve works a little bit differently than a standard mechanically pressure independent valve. An electronically pressure independent valve has a flow meter built into it, and it operates quite similarly to a pressure independent VAV system in that we're simply measuring the flow rate of the water, and we're going to modulate the opening of the valve to accommodate the flow requirement. So the signal from the automation system is interpreted as a specific number of GPMs, and the valve will simply modulate itself to find that number and stay at that number. Since this is not just a flow meter, but it's also a BTU meter, one of the options for the energy valve is not to control to how much flow goes through your coil, but you can control directly to how much power goes into your space. And in addition to these two functions, obviously, your system is dynamically balanced at part load or full load because you're fully pressure independent either in flow control or power control mode. Let's talk for another minute about the difference between position control, flow control, and power control, because I think it's kind of interesting. What you're looking at here is a cutaway of a Belimo CCV, which is a standard pressure-dependent valve. And we could put any kind of pressure-dependent valve on the screen. We could have put a globe valve or any sort of standard type control valve, but we'll use the CCV, and we'll call it position control. And the reason we call it position control is that the control signal sends a signal to the valve that dictates how open or closed the valve is. It really defines the size of the opening that the water has to flow through. So we're controlling the position of the valve. We're not controlling how much water goes through it. We're not controlling how much heat transfer we have. And really, with a pressure-dependent valve, just as the title says, pressure dependent, we're dependent on how much pressure is applied to the water going through that size opening to determine how much flow actually comes through that orifice. So that was sort of the technology for a really long time, but about, I don't know, it's arguable as to when the first PI valve was really used, but we'll call it not so long ago, pressure-independent valves were created and introduced into commercial HVAC systems. And we call those types of valves flow control valves because we're linking the control signal not to the position of the valve as much as we're linking it to how much water goes through the coil. And think about the advantages of having control over exactly how much water goes through your coil versus how open or closed your valve is. In actuality, I don't really care how open or closed my valve is. I care how much heat is exchanged, and the direct result of that would be how much water I put into my coil. And so the new sort of technology that was introduced was this idea of flow control. And flow control is really fabulous. The only thing that really can get in our way is if we're not sure about the temperature of that water. So we know how much water's going through, but what if that water's supposed to be 42 degrees, but it's really 44 degrees? Are we going to get the same amount of heat exchange? And of course, the answer to that is no. And this is where power control comes in. With the Belimo energy valve, you have the option to also utilize power control where we're not going to modulate to a specific flow value, but you can modulate to a percentage of the maximum power output of that coil. So if you have a 5-ton coil, you tell the valve that it's on a 5-ton coil and it modulates from 0 to 5 tons by percentage. And this allows us to be pressure independent and essentially temperature independent as well. Interestingly enough, about all of these technologies, position control, flow control, or power control, is that the energy valve is capable of performing in any one of these types of configurations. So whatever type of control you're most comfortable doing, the energy valve will do it. The most common configuration for the energy valve that we see these days is in flow control mode with delta T limiting. However, we do see quite a few clients moving to power control, and nobody really uses position control other than to maybe create a baseline if they want to see the performance difference from one technology to the next. So that's how we're going to improve our control. And the last point we said as a benefit for the Belimo energy valve was our ability to track your equipment performance. Your system is going to degrade over time. Your coil performance will not be the same in year 3 as it was in year 1. Even if you have a really robust maintenance program for it, it'll still change. And if we're all honest with ourselves, most of us don't have a really robust maintenance program for our coils. And so we would be able to see our equipment degrading, and we can make some adjustments to it before there are any comfort issues, and it's relatively generally accepted that any type of predictive or preventative maintenance that can be done is much less expensive than reactive maintenance. I think we can all agree if you say, hey, that coil's kind of dipping, we should do some maintenance on it during some shutdown time, is much less expensive than 5 guys having to get up in the middle of the night to take care of it, or having to interrupt something very critical in your particular facility to do that maintenance. So again, we're saving energy with the Belimo energy valve, we're simplifying the control and creating you a dynamically balanced system, and we're giving you a BTU meter on every coil that you put one of these guys on, and you can get this instantaneous feedback of performance and long-term logging data. Want to give you a slight teaser about delta T management. The next webinar that we're going to do, and there's a slide coming up that tells you exactly when that is so you can save the date, is specifically about delta T management. But what I want to show you here is some data that came off of an energy valve that was installed at a large tech company in North Carolina. Now, they put quite a few energy valves in this facility, but this is all data from a single energy valve. And what they did was something quite experimental, and it actually follows the chart we showed you before about position control, flow control, and they didn't do power control, but they did flow control with delta T limiting. So each one of the lines that you see here, the bars you see, represents a different control strategy. So across the x-axis, left to right, we have tons of cooling, and then across the y-axis, going from bottom up, we have degrees of delta T, that's chilled water delta T in degrees Fahrenheit. So the first set of data is the gray points in that bottom line, and now there's a smattering of gray points all over this chart, but the clear trend is down here where we have marked it, and this represented what the energy valve measured when it was controlling in position control. So this means it was fully pressure dependent. So it produced between 45 and 75 tons of cooling, and it did it at about 5 to maybe 7.5 degrees of delta T. Now the same valve that was installed on the same air handler was simply reprogrammed to not operate in position control, but to operate pressure independently in flow control mode. Now this was a different period in time, so the loads are slightly different, but we're still in that sort of 45 to maybe 65, 70 ton range. So we're in a similar range, and now we're getting 10 degrees of delta T. So same equipment, same space, similar load range, significantly better delta T performance. The same valve was then, we turned on delta T limiting, and we tinkered with it, and we figured out that we could get 15 degrees of delta T out of that coil and still create the loads required in the space. So again, the loads are slightly different range, but now we're getting 15 degrees of delta T. Let's go ahead and break that down to a specific load point, and that'll give us an idea of exactly what type of energy savings or resource savings we could employ here. We'll call it 60 tons. At 60 tons of cooling, if I do 60 tons of cooling at 6 degrees of delta T, it requires 240 gallons a minute. If I do the same 60 tons of cooling at 10 degrees of delta T, it requires almost 100 gallons a minute less water to create the same amount of cooling with the same equipment in the same space. So we've saved almost 100 gallons a minute. When we put delta T management on and get that delta T up to 15 degrees F, we're able to save almost another 50 gallons a minute. So we started at 240 gallons a minute to create 60 tons of cooling with this air handler in this space, and we finished at less than 100 gallons a minute to create 60 tons of cooling. That's 40% of the original flow value. So you can start extrapolating how much pump head we're saving, the potential impact on your plant between 5 or 6 degrees delta T and 15 degrees of delta T. This is just a little bit of a teaser about delta T performance. Coming up next month at the end of June, on June 24th, I will be hosting a follow-up webinar on saving energy, which is understanding coil efficiency and managing delta T. And this will be a much deeper look at what areas we address with the coil and how we're producing energy savings and how we can go about quantifying the ability to save energy using this particular technology. So thank you for joining me today with the Belimo Energy Valve. We're proud to announce that Control Trends magazine holds the Control Trends Award. Awards every year, and this year the Belimo Energy Valve was announced as the energy saving product of the year. We're very proud of that. The Belimo Energy Valve has received awards all over the world for energy efficiency, and we're real proud of that device. So thank you so much for joining me today. Michaela is going to jump back on the line here, and we definitely invite you to type your questions into the chat window, and we will try to address every single one of them as they come in.
Thank you so much, David. Yes, so if you do have any questions, please feel free to utilize the chat box option, and we will answer those questions as best as possible. Just a friendly reminder, this webinar has been recorded, so that if you joined on maybe during the session and you didn't catch everything, we can surely send you the recorded webinar so that you can view all of it. If after the fact you've completed the webinar, or we've completed the webinar, feel free to email us at marketing@us.belimo.com for any of those questions that you should have after you've viewed the entire webinar. So I do have a couple of questions coming through right now. David, are you ready for some?
Yes, go right ahead.
Okay, the first one is, can the delta T manager be turned off?
Yes, all of the functions for the Belimo energy valve are optional, for lack of a better term. So you can switch between the different modes as we saw earlier. We can go from position control to flow control to power control. The Delta T manager can be enabled or disabled. And what's actually nice about this function is that enabling or disabling Delta T is a BACnet point, as is the Delta T set point. So if you want to do some advanced type of programming, you can really utilize this function to enable or disable Delta T management based on certain conditions you might see within the rest of your system.
Okay, and another question we have, how accurate is the data from the BTU meter?
The Belimo Delta T, the Belimo energy valves measuring equipment is rated at plus or minus 2% accuracy for temperature readings, flow readings, and BTU readings, so the short answer is that we're at plus or minus 2%.
Okay, and we have one more question. Are there any piping requirements due to the flow meter?
Yes, actually, that's a good question. There are. We request that there are 5 straight pipe diameters leading into the flow meter. So if you're looking at the screen right now, water would flow right to left into the energy valve. So the water is going to hit the flow meter first, and we're looking for 5 pipe diameters before the flow meter, just to kind of get a little bit of laminar flow coming in there. It helps the accuracy of that flow reading. There's no requirement on the downstream side, so in my picture on the left side, frankly, once that water goes through the ball valve, it's all mixed up anyway, so there's no sense in putting straight pipe after it.
Okay, and once again, if you do have any questions, there is a chat box that you can type in your questions. We will not be answering questions via the phone, so please go ahead and type in those questions in the chat box. Give you guys a couple of more moments. If you haven't, please go ahead and visit www.belimo.us to take a look at our products, energy valve. You can find more information, some tech documents, some other recorded webinars, and some case studies we have available to you.
And just to piggyback on top of that, there's a specific energyvalve.com website that contains a bunch of case studies and other types of information that are quite useful about energy valve. And frankly, if you want somebody to come to your office or to your facility and give you more information about that, just reach out to your local Belimo representative. If you don't know who that is, send an email to the marketing group or call the Belimo 800 number and just say, hey, I want somebody to come talk to me about energy valve. We'll figure out who that person is and we'll get them out in touch with you. We're happy to come do that.
All right, well, once again, thank you so much for joining us today for the Belimo Energy Valve webinar. Thank you so much, David.
You're welcome.
If you should have any further questions, comments, or if you just want some further information about the energy valve or any of Belimo products, please feel free to email us at marketing@us.belimo.com. I hope you have a wonderful day. Thanks, guys.